Hello, everyone, and welcome. Today, we're diving into a very visual and practical part of functions sketching graphs. We'll be focusing on topic 3B, sketching graphs. By the end of this lesson, you will be able to identify the key features of a graph, use technology to analyze functions, and even construct graphs from a given set of rules. These are essential skills for understanding the behavior of functions. Specifically, our objectives are to identify key features like intercepts, vertices, and asymptotes. We'll then learn how to use our graphing calculators to find these features precisely. After that, we'll practice sketching graphs from scratch using a list of properties, and finally, we'll see how to solve equations using graphical methods. So let's start by defining the essential features we need to look for in any graph. First up are the key features of graphs. The first key feature is intercepts. Intercepts are the points where the graph crosses the x-axis or the y-axis. They are fundamental points that anchor our graph. Let's look at this parabola. The point where the graph crosses the vertical y-axis is called the y-intercept. To find this algebraically, you always set x equal to 0. Notice this point here. This is our y-intercept. It's the value of the function when x is 0. The points where the graph crosses the horizontal x-axis are called the x-intercepts. These are also known as the roots or the zeros of the function, because at these points, the value of the function f(x) is 0. So to repeat, x-intercepts are where the function's value is 0. They are the solutions to the equation f of x equals 0. Next, let's talk about vertices. A vertex is a point where the graph changes direction. These are the peaks and valleys of our function. Consider this curve. It goes up, reaches a peak, and then turns to go down. Then it reaches a valley and turns to go up again. This peak here is a vertex. Specifically, it's a local maximum because it's the highest point in its immediate neighborhood. And this valley is also a vertex. It's a local minimum, the lowest point in its vicinity. Vertices are crucial for understanding where a function increases or decreases. Our third key feature is asymptotes. Asymptotes are lines that a graph approaches but never touches. They act as boundaries for the function. Let's examine this graph. You can see two branches that are guided by invisible lines. This dashed vertical line is a vertical asymptote. The graph gets infinitely close to this line, but never crosses it. This often happens when the denominator of a fraction in the function becomes 0. This dashed horizontal line is a horizontal asymptote. It describes the behavior of the function as x approaches positive or negative infinity. The graph levels off and gets closer and closer to this line. Finally, let's consider symmetry. Symmetry describes whether a graph is a mirror image of itself across a line. In this course, we'll mainly focus on vertical lines of symmetry. For this parabola, if you draw a vertical line through its vertex, the left side is a perfect mirror image of the right side. This red dashed line is the line of symmetry. For many functions we'll see, this line will pass through a vertex or a vertical asymptote. To recap, when we sketch a graph, we are looking for its intercepts, vertices, asymptotes, and any lines of symmetry. These features together give us a complete picture of the function's behavior. Now that we know what to look for, let's see how we can use our Graphing Display Calculator, or GDC, to find these features. Manually calculating these can be tedious, but the calculator makes it much faster. Our objective for this scene is to become proficient at using our GDC to find all the key features we just discussed. We'll work through an example. Let's sketch the graph of the function y equals the quantity x minus 3 divided by the quantity x plus 4. The first step is to enter the function into your calculator. Be careful with parentheses, especially in the denominator. You should enter it as y1 equals open parentheses x minus 3 close parentheses divided by open parentheses x plus 4 close parenthesis. Then press graph to see the initial sketch. Now let's find the intercepts. We'll start with the y-intercept. Remember, the y-intercept occurs where x equals 0. We can use the calculator's value or trace function. If we trace to x equals 0, the calculator tells us that y is negative 0.75, so the y-intercept is at the point 0 minus 3,4. Next, the x-intercept. This is where the function's value is 0. The x-intercept is a root or a 0 of the function. We'll use the 0 or root feature in the calculation menu. The calculator will ask for a left bound and a right bound. After you select them, it calculates the root at x equals 3. So the x-intercept is at the point 3, 0. Now for the asymptotes. Let's start with the vertical one. A vertical asymptote occurs where the function is undefined, which, for a rational function, is where the denominator is 0. Here, the denominator is x plus 4. Setting that to 0 gives x equals -4. If you try to trace to x equals -4 on your calculator, it will show an error because the function is undefined. This confirms our vertical asymptote is the line x equals -4. Finally, the horizontal asymptote. This describes the end behavior of the graph. To find the horizontal asymptote, we can look at what happens as x gets very large, or we can use a rule for rational functions. In our function, the degree of the numerator and the denominator are both 1. When the degrees are equal, the horizontal asymptote is the ratio of the leading coefficients. Here that's 1 divided by 1, which is 1. So the horizontal asymptote is the line y equals 1. Now we have all the pieces. Let's put them together to make a clean sketch. We draw our axes. We draw the dashed lines for our asymptotes at x equals -4 and y equals 1. We plot our intercepts at 0, -0.75, and 3, 0. Then we sketch the two branches of the curve, making sure they approach the asymptotes. And there is our complete sketch with all key features labeled. So, to recap, we can use our GDC's built-in functions to find intercepts, and we can use a combination of algebraic rules and the calculator's display to identify asymptotes. This process allows us to create accurate and well-labeled sketches of functions. Let's continue honing our GDC skills by looking at how to find vertices and lines of symmetry. Our goal in this scene is to confidently locate the maximum and minimum points of a function, which are its vertices, and identify any lines of symmetry. Let's take the function f of x equals x times e to the power of x. We want to find its minimum value and its range. First, we graph the function on our GDC. After graphing y equals x e to the x, we can see that the graph has a clear minimum point somewhere to the left of the y-axis. To find this point precisely, we use the minimum function from the calculator's menu. Using the minimum feature, the calculator finds the vertex at approximately x equals -1 and y equals -0.368. This y value is the minimum value of the function. Since -0.368 is the lowest value the function ever reaches, the range of the function is all y values greater than or equal to -0.368. The minimum value directly tells us the lower bound of the range. Now let's look at a more complex function with multiple vertices and symmetry. Consider the quartic function f of x equals x to the fourth minus 4x cubed plus 2x squared plus 4x minus 3. We need to find all its vertices and its line of symmetry. Again, we start by graphing this on our GDC. The graph has a distinctive W shape, which suggests there are 3 vertices, 2 local minima and 1 local maximum. We can use the minimum and maximum functions on our calculator to find each of these vertices. By repeatedly using the minimum and maximum commands, we can find the coordinates of the 3 vertices. They are a maximum at 1, 0, and 2 minima at approximately -0.414-4 and 2.414-4. Now, what about the line of symmetry? Look at the graph and the coordinates of the vertices. Notice that the 2 minima occur at the same y value, -4. The local maximum at 1, 0 is exactly halfway between them horizontally. This suggests a vertical line of symmetry passing through the maximum point. The equation of this line is x equals 1. To confirm, the line x equals 1 acts as a mirror for the graph. The left side is a reflection of the right side, so we have found our vertices and the line of symmetry. In summary, the GDC's maximum and minimum features are essential for finding vertices. These vertices, in turn, help us determine the range of the function and can reveal lines of symmetry. So far, we've analyzed functions that were given to us. Now we're going to flip the script. We'll be given a set of properties, and our job will be to construct a graph that follows those rules. Our objective is to learn the logical process of sketching a graph based on a list of constraints, like its range, asymptotes, and intercepts. Let's work through an example. We need to sketch a graph with the following properties. The range is f of x is less than or equal to 0, or f of x is greater than 1. There are vertical asymptotes at x equals positive and -2, and the only axis intercept is the origin, which is also a vertex. This seems like a puzzle. The key is to build the sketch step by step. Step 1 is to draw the frame of our graph, which is made up of the asymptotes. The range information, f of x is less than or equal to 0 or greater than 1, tells us there's a gap between y equals 0 and y equals 1, where the graph cannot exist. This implies a horizontal asymptote at y equals 1. So let's draw our axes. We'll add vertical dashed lines at x equals 2 and x equals negative 2, and we'll add a horizontal dashed line at y equals 1. The range also tells us the graph can't be in the space between y equals 0 and y equals 1. Let's shade this forbidden zone. The graph must live entirely below the x-axis or entirely above the line y equals 1. Step 2 is to plot any known points. We are told the origin 0, 0 is an intercept and a vertex. Let's place a dot at the origin. This point is in the allowed region, since f of x can be less than or equal to 0. Since 0, 0 is a vertex, the graph must turn at this point. And since it can't go up into the forbidden zone, it must be a local maximum. This means the central part of our graph, between the vertical asymptotes, must be a curve that comes up from negative infinity along the x equals -2 asymptote, peaks at the vertex 0, 0, and then goes back down toward negative infinity along the x equals 2 asymptote. Step 3 is to fill in the rest of the graph, respecting the remaining rules. We still need parts of the graph in the region where f of x is greater than 1. These parts must exist for x less than -2 and for x greater than 2. So, in the top right section, we'll draw a branch that approaches the vertical asymptote x equals 2 and the horizontal asymptote y equals 1. And in the top left section, we'll draw another branch that approaches the asymptotes x equals -2 and y equals 1. This satisfies all the conditions. And here is a possible final graph. It respects the range, has the correct asymptotes, and passes through the origin as a vertex. This step-by-step process of drawing the frame, plotting points, and filling in the gaps is a powerful strategy. In our final section today, we'll explore a very powerful application of graphing: solving equations. Our objective is to understand and apply two different graphical methods for solving equations, especially those that are difficult or impossible to solve algebraically. Sometimes you'll be asked to find the roots of an equation or the zeros of a function. These terms are closely related. The roots of an equation are simply its solutions. The zeros of a function are the x values that make the function equal to 0. As we've seen, these are the x-intercepts of the function's graph. There are two primary ways to solve an equation like a of x equals b of x using graphs. The first method is to find the zeros. This involves rearranging the equation so that one side is 0. Let's take an example. Suppose we want to solve the equation x squared equals e to the x. Algebraically, this is very difficult, but graphically we can handle it. First, we rearrange it. We subtract e to the x from both sides to get x squared minus e to the x equals 0. Now the problem is to find the zeros of the function f of x equals x squared minus e to the x. We graph this new function on our GDC and use the root or zero feature to find where it crosses the x-axis. The calculator finds a single root at x is approximately negative 0.703. This is the solution to our original equation. This method is powerful because it turns any equation into a search for x-intercepts. The second method is to find the points of intersection. Instead of rearranging the equation, we can graph the left side and the right side as two separate functions. So to solve a of x equals b of x, we graph y1 equals a of x and y2 equals b of x. The x values where the graphs cross are the solutions to the equation. Let's try this with the equation x cubed minus x squared equals 2x minus 1. We'll let y1 be the cubic function on the left and y2 be the linear function on the right. We graph both on our GDC. We can see that the line and the curve intersect at 3 different points. We use the intersect function on the calculator to find each one. By moving the cursor near each intersection and using the command, we find the solutions are approximately x equals negative 1.25, x equals 0.445, and x equals 1.80. This method gives us all the solutions visually. Both methods are valid. Rearranging to find zeros is sometimes simpler, as you only deal with one function. Finding intersections can be more intuitive, as you're directly comparing the two sides of the original equation. All right, let's wrap up and review what we've learned today about sketching and analyzing graphs. We've covered a lot of ground, from the basic features of a graph to advanced problem-solving techniques using technology. First, we identified the four key features that describe a function's graph. We learned to look for intercepts, where the graph crosses the axes, vertices, the turning points, asymptotes, the lines the graph approaches, and lines of symmetry. Then we saw how indispensable our graphing calculator is. We practiced using the GDC to quickly sketch graphs and to precisely find all these key features. This tool allows us to analyze complex functions that would be very difficult to handle by hand. We also developed a logical strategy for a different kind of problem, sketching a graph from a list of given properties. We learned to approach this like a puzzle, first drawing the asymptotes as a frame, then plotting the specific points we know, and finally drawing the curves to connect everything in a way that follows all the rules. Finally, we connected graphing to algebra by learning how to solve equations graphically. We saw two powerful methods: rearranging an equation to equal 0 and finding the x-intercepts of the resulting function, or graphing each side of the equation separately and finding their points of intersection. These graphical methods are vital when algebraic solutions are out of reach. These skills of interpreting, sketching, and analyzing graphs are fundamental in mathematics. They allow us to visualize the behavior of functions and solve problems in a very intuitive way. Great work today, everyone. Make sure to practice these techniques with the exercises.